I'm going to try to do, first of all, let me remind you that this is just the day after the 30th anniversary of the first meeting of the Internet Engineering Task Force, which took place on the 16th and 17th of January, 1986. So there may even be somebody here who might have been there. I think I was there. There were about 20 people around a table. It's gotten a little bigger and more complicated since then. So I'm going to try to convince you of a few things this morning. The first one is that the Internet protocols still have a fair amount of horsepower in them, and that they have had a good deal of lasting capacity to ride on top of almost anything. The second thing I'm going to try to convince you of is that we aren't done yet, and that there is still a lot of work to be done to adapt these protocols to new communication regimes and technologies. I'm also going to try to convince you that TCP/IP is not the end state. It's in fact still evolving, and there may have to be things that aren't TCP or even IP in the future in order to accomplish some of the applications that we are interested in. And finally, I'm going to try to take you more deeply into the future to tell you a little bit about what has happened and what is likely to happen as we experience the rest of this 21st century. So let me start out by taking you back in time. That's pretending that there we are. Some of you will remember the ARPANET. It was one of the first wide area packet switch networks, and it was built on top of 50 kilobit circuits, not even 56 kilobits. It was 50 kilobit circuits. You took 12 voice channels and bonded them together in a Bell 303 modem to produce a 50 kilobit line. And we ran TCP/IP, or at least actually we weren't even running IP on this at that point. We were running the predecessor protocols. But eventually we ran TCP and IP on those 50 kilobit circuits, and that actually worked pretty well. This is what a packet switch looked like back in 1969 when it was first installed at UCLA. It was the size of a refrigerator, and it came encased in a very heavy-duty metal shield because they knew it was going into a hostile environment, namely surrounded by graduate students. So BB&N, Bolt, Beranek, and Newman, that built this, was concerned about that. Here we are in Hawaii, not far from the university. David Laster was here addressing us this morning, as you know. Aloha is a term that sort of means, what the hell? And so basically, the Aloha network said, and this is Norm Abramson and Frank Kuo and Dick Bender and others, figured out that if you just transmitted whenever you needed to, and the receiver confirmed that they got the answer, and if you didn't hear the confirmation, you just transmit again at some random time later, that would work. And of course, a lot of people thought, well, that's nuts. But it actually did work as long as the intensity of the traffic wasn't too high. The story behind, so they used old taxi radios and terminals to transmit and receive data on two frequencies. One frequency was to transmit in to the central facility, and that was in contention. And then the second frequency was to transmit the response back. And since there was only one transmitter on that second frequency, you didn't have any collisions. The little gadget that did the capture of the transmissions was called the menehune, which is Hawaiian for imp. And so they simply adopted the term. What's interesting is that a guy named Bob Metcalf was visiting in Washington, D.C. Not too long after this 1971 period, and he was visiting Steve Crocker, who's the current chairman of ICANN. Steve was then at ARPA as a program manager, and sitting on Steve's coffee table in the living room was a report about the AlohaNet. So Metcalf looks at this, and he figures out, hey, I could do that at a much higher data rate on a coaxial cable. So he goes off and in May of '73 invents the Ethernet, which, as you all know, started out at 3.3 megabits a second, which is dramatically faster than anything else that was around at the time. And it's gone on to 10 megabits, 100 megabits, a gigabit, 10 gigabits, 100 gigabits. So Ethernet has had an enormously long lifetime as well, and IP was put on top of that too. Then in this same general time period, we're talking about the early 1970s, Packet radio comes along. This is partly promoted by the fact that we needed to, if we're going to use computers in command and control, they're going to have to be in aircraft and mobile vehicles and ships at sea, and you can't use telephone wires to connect all those together because the airplanes don't take off very well and the ships get all tangled up. So Bob Kahn started a packet radio program which was adapted in some respects from the Aloha idea as well. So these were running, radios were running at 100 to 400 kilobits a second using spread spectrum technology, which looked like this, a cubic foot size radio that cost about $50,000. So we had a bunch of those in this packet radio van that SRI International constructed, and we went sailing around the San Francisco Bay Area radiating packets, eventually radiating internet protocol packets, linking the networks together. So in 1977, we performed an experiment to link 3 packet switch networks together. The ARPANET, which by this time had been extended to operate into Europe over an internal 9.6 kilobit satellite link, and the packet satellite network, which was using Intelsat 4A sitting over the Atlantic between Europe and the US at 64 kilobits a second, and the packet radio net off in the Bay Area, San Francisco Bay Area. So we ran the San Francisco, or the packet radio van up and down the Bay Shore radiating packets and adapted the routing so that the traffic would go all the way through the ARPANET to Europe, down on a dedicated landline to University College London, then out of the ARPANET into a gateway. We didn't know we were supposed to call them routers at the time, so we called them gateways. And into the packet satellite net over the Atlantic and out through another gateway to the ARPANET again, and then all the way across the ARPANET to USC Information Sciences Institute. So the packets were going from San Francisco to LA, basically. It's about a 400-mile trip, but when you measure the actual packet travel, it was about 100,000 miles because they were going back and forth through 2 synchronous satellite hops and back and forth across the Atlantic and the United States. And it worked. And I remember being pretty excited about the fact that this actually worked because it was mostly software, and it's a miracle when software works. So I was leaping around saying, it works, it works. The satellite link was interesting. We used contention priority-oriented demand allocation, which is a fancy way of saying Ethernet in the sky. So this is the first time that we were able to show that TCP/IP could actually work to link multiple networks using very different transmission technologies at different data rates and different delays and still have an end-to-end functional experience. So the thing that made this all work and the thing that has made IP so attractive is that it basically didn't care how the packets were being carried. It's sort of like postcards that don't know whether they're going on an airplane or a bicycle or a boat or something else. So it doesn't care how they're being carried, and it also is ignorant of what's being carried in the packets. So it's like a postcard that doesn't know what has been written on it. The internet packets don't know what they're carrying, so they don't know what the application is. So the network is agnostic and ignorant of applications. That's been a hugely beneficial ignorance, because it means whenever you wanted to put a new application together, you just did it. The network didn't have to change because it didn't know what the applications were in the first place. So this led to what many of us have called permissionless innovation, which is basically the idea that if you want to do something, just go try it out. That sounds very Aloha to me, too. So we have this tabula rasa, which is just waiting for people to invent new applications. TCP was adapted for reliable retransmission and so on, congestion control, flow control. And we realized that we needed to do some more low latency real-time stuff that didn't matter if the data was lost. The important thing was that it got there as quickly as possible. The military motivation for that was things like radar. You know, you don't want to know where the missile was. You want to know where is it now. And so I don't care if I dropped a few packets, just let me know where is this thing. So UDP was developed after we split IP off from the original TCP spec. The domain name system came along, and the routing system runs in the background. So these things are all designed to build, designed to operate in a very cooperative way, but they create boundaries within which a great deal of innovation is permitted. So of course the internet looks like this now. The important part about this picture is that there are hundreds of thousands of networks, and some of you are operating them, and there's no central control. this is a very collaborative, global cooperative environment. The people who run these networks decide which software they're going to run, which hardware they're going to run, who they're going to connect to, and on what terms and conditions. It's not a top-down design at all. And the fact that it works is simply, I think, it might be a miracle, but it's also the fact that collaborative and cooperative work can be very powerful if everybody adheres to the same standards, which allows for interoperability, which of course is central to internet success. So these are old statistics. You probably have better ones. In fact, this morning I heard someone assert that there were 4 billion users on the net now. I'm glad to hear that, because as the chief internet evangelist at Google, my job is to get more people online. And so if we've gone from 3 billion to 4 billion in the last 10 years, I'm really happy to see that. Of course, there are now more than 7 billion mobiles in the world. And that's more than there are people, so then some people must have more than one. But not everybody has a mobile. But to the first order, that's the leading edge of internet access now, thanks to smartphones. So people who get online often get online with a mobile first and maybe never go to anything else. But again, we're still running and will be running internet protocols, and eventually with the smartphones and LTE, we'll be running end-to-end from one mobile to another across the interior of the internet. So now I apologize ahead of time if I didn't get your favorite transmission technology in this list. It's not intended to, as I think I left out DSL and ADSL and stuff like that. This is not intended to be complete. It's intended to illustrate how amazingly adaptive the internet protocol has been. Namely, it plops down on anything that can carry bits. I think I was fond of observing that all the internet protocol asks that you deliver a packet of bits from point A to point B with some probability greater than 0. That's all it asks. And then we'll build on top of that. So this is a compendium of various kinds of protocols and various data rates that the internet protocol has been able to run on. And I find it fascinating that as time goes on, we discard older protocols and we find new ways to do things at higher and higher speeds and often lower and lower latencies until we finally get to speed of light limitations. So this is just an example. In the future, we're going to be seeing even higher data rates and higher frequencies, like 60 to 80 gigahertz radios, which have the interesting property that the signal sort of gets absorbed in the atmosphere over about a half a mile, which is good. If you want to reuse the frequency, it sort of it creates an environment where you can reuse it without having to go to a great deal of trouble. And I suppose the intelligence agencies like it because the signal disappears after half a mile and you're not visible anywhere. There are some people who are building lights that are doing Wi-Fi instead of Wi-Fi. Many of you, I'm sure, are interested in the Internet of Things, and you see 6LoWPAN and Zigbee and Z-Wave Thread coming from Google. These are all new ways of running the Internet protocol on top of new carrying systems. O3b has been very visible here at this conference. I was quite impressed, by the way, at the Internet Governance Forum last November in Brazil. We asked O3b if they could plop a ground station down right next to the Internet Governance Forum Convention Center, which they did. We were able to demonstrate a 400 megabit service that they appeared to have set up in just a couple of days. And I think I saw a video, maybe some of you also have seen one where they set up a small ground station in not very much time at all. So it was an impressive operation, and pleasing to know that you could reach those speeds to so many parts of the globe, at least 40 degrees north and south of the equator. So this, by the way, suggests to me that we have failed to take advantage of the properties of radio, which is broadcast. And several of us, including Bob Pepper, have thought about this even 20 years ago and didn't succeed in convincing anyone that offering a broadcast IP service would be useful. The idea is simply to say, look, I have this satellite, I can broadcast to 100,000 or 100 million receivers, and if I need to send something to all of them, it's a lot more efficient to do it once than it is to do it 100 million times. And so why hasn't anyone offered a service like that? DirecTV looks like it's kind of that way because it looks like it's using IP, at least somewhere in its implementation. But nobody seems to have offered a simple, straightforward service where you say, you hand me the file and I will deliver it to everybody who can possibly receive it. And if you need to control who actually gets it, you can encrypt it and then allow only the people you wanted to get access to it. So I think we should be adding to the TCP/IP protocol suite a broadcast concept, which my impression is missing. And now Internet of Things is on everybody's tongue and mind these days. I just wanted to emphasize a couple of things. One of them is that as we start bringing all these appliances online, we should be concerned about three things: safety, security, and privacy. We should be conscious of the fact that these devices are going to be interconnecting to other things with multiple radios or maybe even dedicated Ethernet wired connections. Think about it. A lot of these devices already use Wi-Fi and Bluetooth. And there's nothing stopping them from using other transmission systems as well. And so they can be reached in a variety of different ways. Some of them are going to be embedded in homes, in automobiles, in offices, and the like. Some of them may be there for quite a long period of time. I mean, think of the major appliances that you buy today. They typically last for years, if not decades. And so if they have software in them that is required to operate for them to perform their function, sort of like the controller in your car, we have concerns about, first of all, does the software have any bugs? Of course, the answer is going to be yes, because I don't know of anybody who knows how to write software with no bugs. The second question is there any risk associated with it? The answer is yes, because there may be safety considerations associated with the bugs in the software. The third problem is if I find a bug and I need to fix it, how do I do that? And so now this raises the question of how do I update the software in these devices? And that raises yet another question, which is how can I tell that a piece of software which purports to be the right update is actually coming from a legitimate source as opposed to being something from a hacker who would like to take over your refrigerator, or let's say they want to leave the refrigerator alone, but they would like to use it for something in addition to operating as a refrigerator. And when you consider the kind of computers that we have available today, low power, low cost, very, lots of memory, lots of horsepower, you could easily run, Linux or some other, or Android or some other, fairly ambitious operating system in there, do all the functions that the refrigerator requires, and then some, leading to the headline, 100,000 refrigerators take over Bank of America or something like that. So we have serious, it sounds funny, but it's actually a very serious concern. So all of you who are excited about the Internet of Things and have a positive ambitions about it need to be very thoughtful about how to make this a safe and secure environment. It's a challenge for software writers. It's a challenge for people who build compilers and software development systems. It's a challenge for privacy, too. I have, I'll show you a picture. In fact, let me go there. This is a little network that I run in my house. I think many of you have seen this picture before. It's an IPv6 network. It's not me in the garage with a soldering gun. It's a company called Archrock, which was acquired by Cisco Systems some years ago. This is a mesh, an automatic mesh forming network running IPv6 over 6LoWPAN. It every 5 minutes gathers temperature, humidity, and light levels in the house in each room and delivers that to a server down in the basement. Now, I know it sounds like something only a geek would do, but the important thing is you should get good engineering data about heating, ventilation, and air conditioning. So at the end of the year, I actually have good information to decide how to adjust the system. One room in the house is the wine cellar, and as Steve Hooter knows, this is a very important part of the house. It needs to be kept below 60 degrees Fahrenheit and above 30 or 40% humidity so the corks don't dry out. So that room is alarmed if the temperature goes up too high. I get an SMS on my mobile. And occasionally this has happened, where the cooling system goes out and I get an SMS saying your wine is warming up. And if there's nobody there to reset the cooling system, every few minutes I keep getting this note saying your wine is getting warmer. So eventually I called the Archrock guys and asked if they had a remote actuator available, and they said yes. And they said, do you have strong authentication because there's a 15-year-old next door and I don't want him messing around with my wine cellar. So that was a simple project to put in. And then I got to thinking, gee, I can figure out if somebody's gone into the wine cellar when I'm not there because I can see that the lights were turned off and on, but I don't know what they did in there. So my next project, which is well underway, is to hang RFID tags on each bottle. And I contributed some money to a company to develop a handheld RFID detector. So now I can do remote inventory when I'm not at home, and I can see if any bottles have left the wine cellar without my permission. So I was proudly describing this design to one of my friends, and he said, there's a bug. And I said, what do you mean? He says, well, you could go into the wine cellar and drink the wine and leave the bottle there. So now I have to put sensors in the cork. And so if you're going to do that, you might as well go to the trouble of sampling the esters to find out whether the bottle is ready to drink. So before you open the bottle, you interrogate the cork. And if that's the bottle that got too hot, and after the cooling system failed, that's the one you give to somebody else who doesn't know the difference. So this is very important kind of functional capability to have. In all honesty, sensor networks are going to become a very, very common part of the internet. They will be common to most buildings, offices, homes, cars, and the like, to say nothing of the sensors that we'll be wearing on our bodies that are tracking our vital signs on a continuous basis. And I guess I want to emphasize how important continuity or continuous monitoring is. It helps you establish what's baseline, what's normal, so you can then sense that something has become abnormal and maybe do something about it. That's as true for our bodies as it is for our networks and for our appliances and all the other things that we will become dependent on. So although the absolute volume of communication for any one device may be fairly modest, the 20 or 30 or 50 billion devices that may ultimately be part of this environment can generate a fair amount of traffic. So this is just the world as we all see it today, I think. Just standard platforms and application programming interfaces which have opened up a universe of new applications. What's interesting is that the people who write apps for the mobiles don't actually need to know very much about how a mobile actually works. They only have to know enough about the application programming interface to write their software, their application code. And this isolation from depth of knowledge actually contributes to an explosion of applications. Some you'll see financial applications like M-Pesa and others for transferring funds around on mobiles. Mobiles have become controllers. I mean, many of you probably have entertainment systems at home like I do, and it consists of a number of independent boxes, each one of which has its own remote infrared control. And if you're like me, you fumble around trying to figure out which control is the right one to control the box until when you finally figure it out, that's the one with the dead battery. So I conclude we should get rid of all those, use the mobile and the local network to control these devices. And in doing so, create standard interfaces, which means that third parties might be able to offer you a service to manage your entertainment. So you just go to the website, say which movies and music you want, and that service will use its ability to control devices remotely to provide you with that entertainment. It's pretty obvious by this time that if you want that to happen, you need to have good, strong authentication, so only the proper parties are the ones who are controlling the entertainment devices and not the 15-year-old next door. So again, we see that cryptography, digital signatures, two-factor authentication, and other things are becoming vital to much of what we do in this online environment. Google is also trying to contribute to alternative ways of carrying internet protocol with gigabit networks, as you know, in the Google Fiber. Balloons at 60,000 feet, Project Loon, which is still part of Google X, but it might eventually emerge as a real service for people. We invested in O3B. We're happy about that because it's worked out very well for many people. We acquired Titan Aerospace, a drone company, which could be used either to deliver internet services or LTE services or even deliver packages. I'm just waiting for, I had this cartoon in mind where there's a drone that's hovering in front of the door and it sends an SMS saying, hi, I'm in front of the door and I have your package ready. If you don't open the door in 30 seconds, I'm going to blow it down. It's probably not a good idea. We've been experimenting, as have others, with TV white spaces to provide service in the interstices between the normal television channels. And finally, Wi-Fi is going in places where telephone payphones used to go. They still have power, so you might as well just stick a little Wi-Fi base station there and provide access to people. So I want to switch gears now because all of this stuff has worked well with TCP, TCP/IP, UDP, and all the other protocols that are part of the suite. But my colleagues and I at the Jet Propulsion Laboratory started working way back in 1998 on an interplanetary extension of the internet. And we were thinking about this just after the Pathfinder project landed successfully on Mars in 1997. It's a little robot. And it was transmitting data directly back to Earth from the surface of Mars. And we got to thinking, you know, this is really a weak reed on which to build space exploration, to have point-to-point radio links carrying all the data. What if you had something like the internet to link all the planets together and provide support for manned and robotic space exploration? It would be much more resilient, just as we use internet today. So we started out thinking that we could just use TCP/IP, right? Because it worked on Earth, so it ought to work on Mars. The thing that we hadn't quite figured out was what the speed of light delay was going to be, you know, between Earth and Mars, for example. And you know how to do the math, right? The speed of light is too slow. The closest we are together in our orbits is 35 million miles. That's 3.5 minutes one way. And if they're farthest apart in their orbits, it's 20 minutes one way and 40 minutes round trip time. And I guarantee you TCP/IP flow control was not designed with a 40-minute round trip time in mind. So we had to develop a whole new suite of protocols that took into account disruption and delay. Now, the disruption should be pretty obvious. There's this thing called celestial motion. You know, the planets are rotating, and we don't know how to stop that. So if you're talking to something on the surface of the planet, and the planet rotates, eventually you can't talk to it until it comes back around again. This is also true of orbiters. So that's the disruption part, and the delay is obvious. It's variable delay on top of everything else, and it's very big. And it gets worse and worse as the speeds go up. And recently, you know, most of these systems have been running on radio links that might give you, you know, even a megabit if you were lucky. But just recently, this was last year, NASA performed an experiment with an optical laser to the moon at 600 megabits a second. So if we could get enough power on a laser on Mars, we may be able to transmit data at literally hundreds of megabits a second. And that might be a big improvement in terms of data gathering, but it also increases the delay bandwidth product for the protocols that we're running. When the rovers landed on Mars in 2004, in January, the original plan was to transmit data directly back from the spacecraft to the surface of Earth, to the Deep Space Network, the big 70-meter dishes in Canberra, Australia, Madrid, Spain, and Goldstone, California. The radios overheated. They had to reduce the duty cycle, and the scientists were all unhappy because they were only getting 28 kilobits a second in the first place. So one of the engineers at JPL said, well, we have an X-band radio on the rover, and we have an X-band radio on the orbiters, but we can't go all the way to Earth with the X-band radio, but we could go up to the orbiter. And the orbiter had a transmitter that could go back to Earth, and since it was out of the atmosphere and with larger solar panels, it had more power. So we could go 128 kilobits up to the orbiter and 128 kilobits back to the Deep Space Network. So we rewrote the software in the rovers and in the orbiters to do store and forward. So 99.9% of all the data that's come back from that mission has come back through a store and forward network running what we call the prototype of the bundle protocol. Basically, it's a store and forward protocol that takes into account variable delay and disruption. The same protocol showed up on the Mars Science Lander. It's now running on the International Space Station. We had some experiments with the astronauts using the bundle protocol to control a rover on the surface of Earth in Germany. Just the original one was just a little Lego rover, but the idea was that the fact that these protocols were designed for delay and disruption tolerance didn't prevent them from being used in real time when the actual delays were low. So that software is now being used not only to do real-time control, but to carry voice and data and video, as long as the data rates are high enough and the latency is low enough for those applications. We have new projects underway at JPL and elsewhere in Mars in 2020, when there'll be a mission sent to Mars to gather samples which will be left on the surface until another mission can come and pick them up and return them to Earth. So sometime during the next decade, we may actually get a chance to have significant amounts of samples of the Mars material, just as we got material back from the moon way back in the late 1960s. So we hope, frankly, that now that these protocols have been standardized by the Consultative Committee on Space Data Systems, that we will be able to standardize the protocols that are used for all the space missions that come in the future. And even if those protocols are not specifically used for the scientific mission, once the mission is completed, those spacecraft could be repurposed as routers in a store and forward network, just as we repurposed the orbiters around Mars, which originally were used to map the surface of Mars, and now they're being used as communication relays. So we could imagine accreting over time an interplanetary backbone as these missions get launched. So that's our aspiration anyway for these new brands of protocols. The other thing I wanted to mention, though, is one other project. It's called the 100-Year Spaceship Project, and this was funded by DARPA, which, as you know, funded ARPANET and the Internet, and in fact funded some of the original interplanetary Internet architecture and protocol development. The problem here is to get to Alpha Centauri in 100 years' time. And we have a couple of problems to overcome. The first one is propulsion. With the current propulsion systems, it would take 65,000 years to get to Alpha Centauri. It's a little long even for an ARPA project. So we're going to have to do something about that. The likely outcome will be ion engines. The question is, what's the power source? There are some very impressive ion engines now using xenon, which gets ionized. And more recently, one design uses solar power in order to ionize the xenon that gets expelled out the back, and that gives you thrust. In order to travel farther, what does that mean when it goes away? I should stop. In order to travel well beyond the sun's envelope, you're going to have to do something besides sun power, and so people are now looking at fission and fusion products. I've seen some very interesting fusion designs recently. You know, this has always been a will-o'-the-wisp that's receding at the speed of light. It's now getting to the point where fusion may actually be feasible. And so I've seen some very, very impressive work. So we might end up using a compact fusion engine in order to drive this thing. We'll probably have to get up to about 20% the speed of light at the 50-year mark. Of course, then we should slow down after that, because if we don't, we'll be going through Alpha Centauri at 20% the speed of light and get one picture if we're lucky. So we'll have to slow down and go into orbit. And then there's the navigation problem is interesting because nothing is where it looks like it is. You know, you understand the stars are, because of the speed of light delay, they only look like where they were, you know, when the light originated from them. So, you know, how we normally do interplanetary navigation, you get part of the way there and you do mid-course corrections, and, you know, there's round trip times are significant, sometimes hours, but that's not impossible. But imagine that you have a spacecraft that's a light year away. It takes a year to say anything to it and another year to find out what happened. This is not very interactive. So we're going to have to do some kind of onboard navigation. This is not crazy because the stars that are far away and bright can be used as navigational signposts, and the spacecraft should be able to find its way to Alpha Centauri. My problem, of course, is communication, and the question is, how do I communicate from 4.3 light years away? How do I generate a signal that's going to be detectable? One possibility is a femto or attosecond laser, you know, where you take 100 watts of energy, compress down to 10 to the minus 15 or 10 to the minus 18 seconds, which gives you a very big signal, which should be detectable from some light years away, except for the one thing: even if it's a collimated laser, the laser beam is going to spread. So by the time it gets back to us, you know, it will have spread out to about the size of the solar system. Now you know why I need an interplanetary backbone, because I have to build a synthetic aperture receiver that'll reintegrate the signal coming back from Alpha Centauri. One of the guys, however, in the project points out that the sun's gravity will bend light. You'll all remember that that's how Einstein's theory was at least confirmed, because he predicted that light would bend in the presence of the sun's gravity. So if you go 550 astronomical units away from the sun, you get to its focal plane, its gravitational focal plane. So you can imagine putting a spacecraft at the right place, in 550 AU away from the sun, which is about 55 billion miles, and then use that to reintegrate the signal coming back from Alpha Centauri. So this actually would be a good thing to test the ion engine, right? You could send something out at, to 55 billion miles away. The spacecraft which has gone the farthest so far are Voyagers 1 and 2, which are about 13 billion miles away, and it took them 33 years to get there. So I hope that we're able to get that ion engine sooner rather than later to test this idea out. So that's the up-to-the-date statement of where the 100-year spaceship project is and its communication requirements. I'm going to stop there. It looks like I got a few time for some questions. I think I have my interrogator coming, and I will thank you very much for your time.
Let's have a round of applause for that. Thank you. So I guess now we have the plan for the new Google autonomous vehicle program. It just isn't self-driving cars. It's
a self-driving spacecraft.
Exactly.
That's it. Right.
So we're going to open it for questions. I have a few questions for you, and you can submit your questions either by raising your hand and getting mic or through Siftly. But the first question I want to ask you isn't really necessarily a technology-oriented one. It's more a personal one, which is if you go back to 1977 or so, you're an engineer, you're working with Bob Kahn. I picture sort of this was probably even before whiteboards, I picture blackboards, and you're kind of figuring out how to map TOS bits across protocols. Did you anticipate Snapchat and Facebook, or, I mean, how were you thinking about it at the time, and how did the, evolution work?
Well, I think that we were not considering specific applications, but we were certainly considering generic kinds of things. For example, voice and video were part of the program. We were experimenting with packetized voice in the 1970s on the packet radio system, on the ARPANET, and eventually on the internet. It was very funny, though, when we were first doing this, because remember the 50 kilobit backbone on the ARPANET? We were trying to do packetized voice, and normally digitized voice is about 64 kilobits, 8,000 samples a second and 8 bits. Maybe use differential encoding, you get to 32 kilobits. We only had 50 kilobits to work with. So we decided we'd better use a higher compression system. So we used something called linear predictive code with 10 parameters, which models the voice tract as a stack of 10 cylinders that are varying in their size as you speak, excited by a formant frequency. So anybody that spoke through this particular LPC-10 system sounded like a drunken Norwegian. But understandable. But so one day, I'm at ARPA by this time, and I had to demonstrate this packet voice system to the generals over at the Pentagon, and I remember thinking, how am I going to do this? And I remembered that one of our collaborators was Ingvar Lund from the Norwegian Defense Research Establishment. So we got Ingvar to talk through the normal voice system, then we had him talk through the packet voice system, and it sounded exactly the same. We just didn't tell the generals that everybody would sound that way. So we were doing video, we were doing voice, we were clearly doing data of one kind or another, file transfers, email, all that stuff. Even real-time interaction that you would think of as instant messaging, we were already doing that way back even in the ARPANET days, where you would telnet to a common machine and then type at each other. So the honest answer is that we saw the fundamental capacity to do a wide range of things that we do today. And to be really honest with you, almost all the stuff that I see today, Snapchat and instant messaging and everything else, looks kind of like variations on email or telnet. So even though people who invent these new things imagine they're brand new, I think their origins are actually in the distant past.
So there's a question from Siftly on where you see the division between wireless and landline for the last mile of internet traffic.
Well, the obvious division is one is wireless and the other one doesn't.
Well, I assume it's a fraction of traffic.
Right, yes. Yeah. Oh, I see. Okay. Yeah. That's really interesting. The reason that's so hard to answer is that it depends on where the traffic's going. So if the wireless traffic is actually just kind of local, think of all the traffic that must be in your house that stays among the various devices in the house, like to the printer and so on, compared to the stuff that actually goes out into the public internet. We used to see incestuous traffic as like 2/3 of all the traffic was very local and 1/3 of it was across the net. I think it's probably changed substantially now, especially given the streaming video. But even that is starting to move more local, not absolutely local, but more local, because content distribution networks are becoming more common. And so we try to, anyone with a right mind is trying to avoid transmitting huge amounts of data all the way across the global internet if you could avoid that. So on the wireless side, almost everyone's access today seems to be increasingly wireless. I don't see a whole lot of dedicated Ethernet for local access. But ultimately, all of those wireless systems have to go to ground, have to get onto backhaul, typically onto fiber. So again, no one has enough data to calculate that split, and I certainly don't. But I'm sure that locally or nearby, it's all going to be wireless, and then for long haul, it's going to be on the fiber, whether it's underground or not.
Looks like maybe for Netflix and YouTube, right? Because Netflix and YouTube already are 50% of edge access bandwidth at peak.
It is, but let me remind you that back in the earlier days of internet, let's say after 1983, when it was first turned on, that the bulk of the traffic was email, because these other applications hadn't come along. And so I'm hesitant to use any of the existing data, including Netflix and YouTube, to predict much about the future, because there may be new applications that might require even more data rate, or we may find ways of doing compression. So we shouldn't, okay.
So speaking of those...
Well, what was the question? Here we are.
Okay, so there's another question, which is a typical question around net neutrality. And what's your position, I guess, and by you or I'll say Google's position on net neutrality, and how does that impact the evolution of new applications, as well as the kinds of things that you'd want, like preferential treatment potentially for high QoS demanding apps?
So is Bob Pepper still in the room? I was hoping that Bob would leap up and respond. Okay. So let me say a little bit about this. In the US in particular, this net neutrality debate was partly a consequence of the limited amount of competition for broadband service offering. I mean, it used to be, when we were a dial-up internet, that we had 8,000 internet service providers. And if you wanted to switch providers, you just dialed a different number. And so there wasn't a big deal about switching. But with broadband capability, you required special equipment at home. Somebody in a truck had to come out and install it. If you wanted to switch, somebody else in a truck would have to come out. And so most users ended up with one or two choices for broadband service from a telco and from a cable co. If you were lucky, and in some places in the rural parts of the country, you didn't have any choice at all. So net neutrality, from my point of view, has always been about inhibiting the ability to abuse control over that broadband channel to limit what users were allowed to choose to do, either what applications they ran or where they went on the network and what it cost them to go to wherever they wanted to go. The control over that broadband channel without much competition could lead to unfairness with regard to the consumers and sort of a competition problem. So I've interpreted the FCC decision to treat internet service not as Title I application, but rather as a telecommunications service in Title II, as an attempt to root their net neutrality concepts in a legal regime which does give them the authority to exercise the net neutrality rules. I'm no longer persuaded that the QoS stuff is as critical as people seem to think it is. And that's a controversial area. But you know, as the speeds go up, the concern over quality of service should go down. And certainly in my world at Google, where we're offering gigabit per second service, there's a lot you can do at the same time without much interference.
So one last question for you. As you look towards the future, I guess, what is it that excites you the most? Because you have this broad purview from literally day one of TCP/IP till now, and there's so many things going on between quantum encryption and Internet of Things and interplanetary communications. So what are you Like, what grabs you the most? What do you ponder?
Well, I think what is most important to me is that people not come to the conclusion that we've come to the end of the design, that there is no new idea coming along. I want, especially young people, to feel very comfortable saying, this TCP/IP stuff was designed 40 years ago. I have some new ideas. I want them to pursue those ideas. I want them to feel empowered to try out some new things. This net should not stop evolving. And so, and it won't, because people will have good ideas. So I'm more excited about the future and new ideas, even though I'm certainly glad to know that the protocols that Bob and I worked on, and many others did as well, have served us for quite a long time. But they won't serve us forever. We have to put new ideas in place, and I can hardly wait to see what they are.
Okay. Well, it's been a great honor to have you. Thank you so much for making the trek out here, and let's do it.